Okay, welcome to the second example in chapter 3. The question reads, the pole supported by a pin at point C and an A36 steel guy wire AB. If the wire has a diameter of 50 millimeters, determine how much it stretches when the horizontal force of 11 kilonewtons acts on the pole. Okay, so right off the bat, we're given a bunch of information that we can write down, namely that the diameter of this wire that we're trying to find the change in length of has or is 50 millimeters. This force that acts on the pole that's attached to the wire has a magnitude of 11 kilonewtons, and we're also given the material of this wire. And the question says that it's A36 steel, and from now on, once we're given the material, we can derive several properties from it, right? Or we should know what properties are associated with this specific material, whether it be the elastic modulus or something like Poisson's ratio or stuff like that. And in this case, A36 steel typically has an elastic modulus of a nice round number of 200 gigapascals. Perfect. We can also find this length, L naught of wire AB, but I think we'll keep it to a bit later. But we are eventually going to find it. You could find it easily from here, just using cosine in this case, right? But we will get to that. In terms of unknowns, this question wants us to find the change in length of wire AB once this force is applied, right? We did a very similar problem back in strain, but now we're going to use the elastic modulus. So that's how this question is a bit different. I think you were given strain in that problem, whereas this one, we have to find it using this lovely guy. Okay, so we can write that down. The change in length of the wire AB, spoiler alert, is equal to strain AB multiplied by the original length AB. How do we find this guy? Well, you can easily find it geometrically. We will do that. Wait 1 second, please. For the strain, we're going to use the elastic modulus is equal to stress over strain. How do we find stress? Well, we're going to get into that. So basically you can find this. So hold your horses. We will get to it. To find stress eventually, we're going to need to know the magnitude of this force right here. This force that is in the wire. Why do we need that? Well, if you think back to stress, stress is equal to the force causing the stress divided by the cross-sectional area. The cross-sectional area in this case is equal to pi over 4 d squared. We have all this information. We need to find the force. How do we find the force? Well, we use a beautiful free body diagram. I haven't done those in a while, so we'll speed through it. So, free body diagram. If we draw this lovely guy right here, this is FAB, your force, right? Let's say right here is your 11 kilonewton force. And from here to here is 1 meter. From here to here is 1.5 meters. This is your point C, right? This is your point B, right? How are we going to find this force FAB? Well, right off the bat, when I look at it, I think I can take a moment about C, right? And then using that, I can find, and oh, there's one more information I didn't put down. This angle right here is 30 degrees, right? So let's take a moment about C. If I take a moment about C, and we can say that counterclockwise is positive, what forces cause a moment about C? Well, this force will cause a moment about C, right? It'll cause a negative moment, so 11 kilonewtons. Don't forget to convert it to newtons, multiplied by 1.5, right? Plus, this component of FAB is gonna cause a moment, right? How do I find this component? Well, it's simply FAB sine, FAB sine of 30, right? Not the actual force, the component of the force is going to cause this moment. Because if you see this component of the force, it's parallel to the distance. So, yeah, but this is just a review, hopefully. Okay, so FAB, the force, sine 30, multiplied by the distance, and in this case, it is 2.5 meters. From this, you can easily find FAB, and you'll find it to be, don't forget to convert this to newtons, you find it to be that it is of magnitude 13.2 kilonewtons. Right? Beautiful stuff. Okay, now we can actually find, or we can start solving for our unknown because we have all the given values. So we want to find change in length of wire AB. You could have, if you wanted to, if you didn't know that you had to do this, you could have went straight to this. And then once you get to the part where, oh, I need force FAB, then you can go through this process. Like, yeah, I guess that's also a better approach, but we did it first. So it doesn't really matter about the order. Okay, we can start with that branching method we always do. So the change in length of the wire AB is equal to the original length of wire AB multiplied by the strain in wire AB, right? How do I find the original length of wire AB? Well, if I look back up here, right, I want to find this guy, right? This is length wire AB. How can I find it? Well, I know that this angle right here is 30 degrees. I know that this distance right here is 2.5 meters, right? What is cosine equal to? Cosine is equal to adjacent over hypotenuse, right? And if I apply this formula to this case right here, I'm going to get that cosine of 30 degrees is equal to adjacent 2.5, or, yep, 2.5 meters, divided by LAB. I rearrange a bit, I will get that LAB is equal to 2.5 meters divided by cosine of 30, square root 3 over 2. Yep, square root 3 over 2. So we can rewrite that. Actually, let's rewrite it in the proper colors. So delta LAB is equal to 2.5 meters divided by, let's keep it as cosine 30. Now we need to find the strain. How can I find the strain? Well, as we said previously, the elastic modulus is equal to stress over strain, right? What is stress equal to? Well, stress is equal to a force over an area, right? Let's further simplify this. What force are we talking about? Well, the stress for this wire AB is equal to the force AB, which we just calculated, right? Divided by the area of wire AB. What is the area of wire AB? Well, I was given the diameter before, right? So it's simply pi over 4, the diameter of wire AB squared, right? All the way back to stress. Very similar, or the exact same concept, which we did before. Okay, now I have the stress, right? And we'll write all this stuff down. This is just the concept. Do I have the elastic modulus? Yes, I do. It's 200 gigapascals because I know the material, right? Therefore, I can easily find strain. I can say the strain is equal to stress over the elastic modulus, right? Okay, let's write all that beautiful stuff down. So I know the strain, AB, is equal to stress, AB, over the elastic modulus. I know that strain AB is equal to the force AB divided by pi over 4, diameter AB squared divided by the elastic modulus. And if I keep simplifying, I'm going to get that my strain AB is equal to force AB divided by my elastic modulus multiplied by pi over 4 multiplied by my diameter squared. Right? If I plug all those numbers in to this formula, I will end up getting, let me just move this stuff over a bit. I'm going to end up getting, my force is 13.2 times 10 to the power of 3 newtons, right? Divided by my elastic modulus, which is 200. It should be megapascals, but I'll keep it in gigapascals because of the space. Multiplied by pi over 4. Multiplied by my diameter of the wire, which is 50 millimeters, right? 50 millimeters squared. And perfect. You have all your values, and now you can just plug and chug. But remember, this is megapascals, or it should be in megapascals. So when you plug it into your calculator, it should be 200,000 megapascals if you want the correct answer in the end. So once you do this beautiful calculation, you're going to end up getting that the change in length of your wire AB from this setup is going to be 0.09704 millimeters. And that is the answer to this question.